Hello, I'm Carla Moldaven, and today we're going to look some more at mathematical modeling. In another video, we looked at density and mathematical modeling of how the volume and the weight of some mineral samples compared. I'm going to describe for you today 3 experiments that I hope you can either do on your own or perhaps in your class time, and look at the relationship between the variables in these 3 experiments. The first one is the viewing tube experiment. For the viewing tube experiment, you will need some meter sticks, measuring tape, and some cylinders that are open on each end, like a cardboard roll from wrapping paper or paper towels or something like that. And we'll illustrate this in just a minute. And you will have students work in groups of 3 would probably work best. One student is going to look through the viewing tube, and another one holds the measuring tape against the wall, and one student records the data. And if you have time, you could exchange roles once you've collected the data from one person doing the viewing through the tube and let somebody else do it and see if you're getting comparable results. So what we want to explore is how does the number of centimeters one can see through a particular viewing tube vary according to the distance from the measuring tape. So let's make sure that you understand the setup for this by looking at a volunteer helping me here to do this experiment. First thing we will do is to take our meter stick and lay it down in the floor from the wall 1 meter, so that my person who's going to be viewing is going to stand 1 meter back from this wall. And he's going to look through the viewing tube, and my tape measure is 1.5 meters, and it's convenient because each decimeter or 10 centimeters is marked with a different color. And Brian is going to look through the tube so that the top of it is going to match there with the top of the measuring tape. And he's going to tell me how many centimeters he can see. And if it's hard for him to read that, which it would be for me, he can sort of tell me how far up or down to move my finger to show where he can see too.
I can see it. I can see 8 centimeters.
Okay, so Brian can see 8. So I would record on my data sheet that from 1 meter back from the tape, he can see 8 centimeters. Then what I would do is go down and flip over my meter stick that's down here so that he knows where it would be 2 meters back. And he'll do the same thing, tell me how far he can see this time.
I can see, looks like 15 centimeters.
15, okay. And if you're doing this experiment, thank you, Brian,
You're welcome.
you would collect the data not only for 1 and 2, like Brian did, but also go back for 3 and 4 centimeters. What do you expect your results to be? This is the instructions again about standing back the distance from the wall. And one group member stands and looks at it, and the other one determines how far can be seen, and then one person records the data. So this would be an example of a table that you could record your data in. In our case, we would have had that Brian could see 1 centimeter, from 1 meter back, he could see 8 centimeters. From 2, he could see 15 centimeters. And he would repeat it for 3 and 4 if he were you actually doing this experiment. So once you get your data, you would then go to your calculator and find your line of best fit for it. And I have just made up an equation for a line of best fit here because I want to concentrate on the interpretation of it. Suppose that somebody tells you that the theoretical model for their viewing tube experiment would be y equals 14x plus 2.5. My question is, what would the 14 represent on this? You know from your experience with linear equations that if you have an equation in the form of y is equal to mx plus b, that the m value represents the slope. But most of the time you've been taking a very abstract approach to that. And what we're trying to do in these modeling experiments is to think about what does that slope mean. This would be saying the change in y related to the change in x is 14. That would be saying every time I go back an additional meter, I can see an additional 14 centimeters. What would the 2.5 represent? Well, that's the y-intercept. That's what we get when the x value is 0. What would it mean to be standing 0 meters from the wall? I'd be right up against the wall, wouldn't I? If I could shorten the viewing tube, then I would be seeing just the diameter of that tube. So I would be saying that that would mean that the diameter of the tube theoretically would be the 2.5 centimeters. So from this, I want you to grab hold of the idea of taking your model and interpreting in the physical context, what does the slope mean? What does the y-intercept mean? So if you take your data and you went back, and I got Brian to do this, it looks like he could see an additional 7 centimeters the first time he stepped back. Do you think he'd be able to see an additional 7 the next time, or would it be more, or would it be less? Well, let's just make up numbers here and say he saw 8 more and he saw 23. And then maybe he sees 7 again and he sees 30. My point in doing this is to say, again, with real life data, this isn't going to be perfect. So the 8 and the 7, they're not exactly the same, but they're close to being the same. So it looks like the rate of change is constant, almost the same each time, which suggests to me that this is a linear relationship. Notice too that we're taking one particular viewing tube, so you're looking at the results from your tube. Somebody else might get different results. Their tube will have a bigger diameter. They'll be able to see more. But in all of them, you should be expecting this additional number of centimeters that you can see as you go back an additional meter to increase by about the same amount. The next experiment that would be nice for you to try is the ball bouncing experiment. So we want to look at what is the relationship between the height from which a ball bounce is dropped and the height that it bounces. So again, I'm going to need a meter stick, and I've got some little rubber balls, and I'm going to place the meter stick so that the 0, 1, 2, 3 are down here on the floor or the table, whatever you're going to use to bounce against. That'll make it easier for me to read the numbers. And what I'll do is on my X value, my independent variable, I'll be recording the heights from which I dropped the ball. So you can do them randomly, or you can make a systematic chart. You could start out at 10 centimeters and 20 and 30, or you could start out at 100. And you're going to have one person holding the meter stick and another person dropping, and then somebody who's got the hard job has to try to see how far did that ball bounce. So Brian's going to help me again here. He's going to come over here, and I'm going to try dropping it from 20 centimeters. And Brian estimates it was about
I think it bounced up to about 15.
15, okay. And we'll try one more just to get the idea of it. For 30 centimeters,
Looks like it went up to about 23.
okay. Now, the amount that it's going to bounce up is going to vary by whether I'm using this table or whether I put it on the carpeted floor. And it would vary from ball to ball, and it might vary according to the temperature. So you've got all kinds of variables thrown in there. And what you're saying in the experiment is that you're controlling for all those variables except the height. So I'm only using this to bounce off of, and I'm only using this ball. What do you expect is going to happen on that one? Got any ideas? These were our instructions again about how to do the experiment, holding the meter stick, holding the ball and dropping it, and another one observing to see how high it goes. So my data sheet would look something like this. Brian said when I dropped it from 20 centimeters, he thinks it went up about 15. When I dropped it from 30, it went up to about 23. And again, how far it would actually bounce is going to depend on the surface you're bouncing it off, so we're holding that constant. So you would continue collecting several data points and then ask yourself, does this look like it's a linear relationship or not? What I would like for you to do if you gather that data, again, is to put the data in the graphing calculator and then get your line of best fit, because it should appear that your data is approximately linear. And then describe verbally and with an equation the relationship that you have observed between the height of the ball when you drop it and the height that the ball bounces. In some cases, when I've done this experiment with certain balls and certain floors, I might get an equation like y is equal to 1/2 x. What would that be saying? X, my independent variable, is the height from which the ball was dropped. And y is going to be the height that the ball bounced. So if this turned out to be my results, I would have the height that it bounces being approximately half of the height from which it was dropped. So if it were dropped from 40 centimeters, it would be bouncing up to about 20 centimeters. If it were dropped from 80 centimeters, it would be bouncing back up to about 40 centimeters. Now for Brian's, we had at 20, it was bouncing back up to 15. If that pattern continued, then I would be saying the ratio of 15 to 20, that would be 3 to 4. So his equation might turn out to be y is equal to 3/4 x. The third experiment that I want to describe for you is involving melting ice. And I'm asking a question that we probably don't know the answer to unless we've done the experiment already. Does ice melt at a constant rate? And you might want to think about that for a minute and make a conjecture and explain what you think, explain your reasoning. Some people think, well, as it gets to melting, it starts going faster, and they put in some reasoning about the surface area and things like that. To do this experiment, what you're going to do is to take a graduated cylinder, and you're going to take a funnel and fill the funnel with ice, and you're going to put the funnel on top of the graduated cylinder so that you'll be able to measure the water from the melted ice that collects in the graduated cylinder. And every 5 minutes, check the amount of water in the graduated cylinder. So we are asking if it is a linear function of time. Is the amount of ice that has melted, the number of milliliters of water that has collected, going to be directly proportional to the amount of time? If we had started at 0 time and we just had ice, there would be 0 melted. Suppose after 5 minutes, I've got 5 milliliters of water. And after 10 minutes, I have 10 milliliters of water. And after 15, I have 15, and so on. Then the equation for that would be y is equal to x, and your slope would be saying that for every minute you're getting 1 additional milliliter of ice that's melted. So it is a linear relationship. So in the experiments that you've done today, you may think, well, everything turns out to be a linear function, but no, of course it doesn't. Later on, you'll be looking at some exponential models and logarithmic models and logistic and rational. So there's all kinds of different relationships. But the thing that you want to think about is, if I've got some data that I'm trying to analyze, how is it I decide if it's linear or not? If I have a table of values, let's say that I give you some numbers here. I'll use 0, 5, 1, 8, 2, 11, 3, 14, 4, 17. And right now I'll go back to being abstract again, so I haven't told you what X and Y represent. But suppose this is some real world data that I'm trying to analyze. How do I know if this fits into an equation of the form y equals mx plus b? How do I know that the independent variable x and the dependent variable y have a linear relationship? Well, the thing I look for in the table is that constant rate of change. As the x values are going up by 1 each time, what's happening over here to the y values? They're going up by 3 each time. So it's that constant difference that lets me know it's a linear function. Furthermore, where does that constant difference go in the equation? That's the slope. That's the rate of change. So I would have y is equal to 3x plus b. That constant rate of change is the slope. And since b represents the y-intercept and 0, 5 is the y-intercept, that means that my 5 would be the value for b there. So you could go back and check each one of these to see if they satisfy that equation. For example, if I check the 4, 17, 17 is the y value, 4 is the x value, 3 times 4 is 12, and 12 plus 5 is 17. So you're very comfortable with taking an equation like 3x plus 5 and coming up with a table of values and graphing it. And this time, in terms of modeling data, you would be collecting the data and you're trying to decide based on that data, is it linear? So you're looking to see, is there that constant rate of change there? From the graph, if you were modeling data, you're looking at your scatter plot, and you could do that on your calculator real easily, and you've got your points here, and they don't exactly lie on the same straight line because of inaccuracy of measurement and other things like that, but they do tend to be close to the same straight line, and I can find that line of best fit. So I can look at the data points and see, does it appear that they all look close to lying on the same straight line? From the equation, of course, you know that if it's in the form of y equals mx plus b, that it is a linear relationship, a linear function. So again, we've modeled some different situations with physical context, thought about the meaning of the slope, and we've recognized the fact that, yeah, we've done a lot of examples of linear relationships, but not everything in life is linear. So you can look forward as you continue your study of mathematics to look at other kinds of functions and model those. Thank you.